sorry, we got the little controls up there. We'll just have to live with it.
Thank you.
Matt will make sure we're not distracted too much. All right, thanks.
All right, thanks everyone. Thanks for coming in. Thanks for dialing in on the phone. I'm not sure how close to the need. You know, you could just stand here. So first, let me acknowledge my collaborator, Terrence Savitsky, from the BLS, Real Labor Statistics, right here in the building, and I'm from National Center for Science and Engineering Statistics. So we worked on a couple papers together, and this is sort of an extract of that. Okay, so what do you do with what do you do with data from a complex survey design, right? So one goal could be you have a model that you want to fit, and you have some hypothesis about the underlying population. So that's the goal. You want to fit a model. But in practice, the data comes from a complex survey sample. So that means that the chance of being in the survey is actually related to the outcome. It's called informative sampling. So that means if you look at the distribution of the data in the sample and the population, they're different. Often they're very skewed compared to each other. So if we ignore that difference and we just try to do our regular model fitting and estimation on the sample, pretending it looks like the population, we get biased estimates. We get biased results. So one way around that is to use the probability of being included in the sample as a weight, as an inverse weight, and that mitigates a lot of the bias. But what we're left with is we still don't have the right standard errors. So our confidence intervals of tests and things will be incorrect. So this talk will, at a high level, talk about how we can get some approximate ways to get the correct uncertainty quantification, the correct standard errors. So variance estimation for surveys, there's really the de facto approach. You can see different ones in the literature. The de facto approach is to assume that you have independence at the largest clusters, the primary sampling units. So that could be a geographic area, that could be a household, that could be maybe a business. And within clusters, any subsampling, essentially the dependence is treated as a nuisance. You just try to aggregate up. There's two common methods to do this called Taylor linearization and replication-based methods. That's what we'll talk about today. And there's a variety of different flavors or variations, but they basically amount to these two techniques. So Taylor linearization. So we start with outcome we're looking at is Y, some covariates X, and the weights that are based on the survey design, or W. And we want to estimate, we want to look at parameters theta. So for Taylor linearization, you take this estimate, theta hat, or a centered estimate or residual, and you approximate it as a weighted sum. So it's a linear operation of weights. And this Z is just a function that's evaluated at the data and your sort of point, your best estimate. What you do is you take this larger sum and you decompose it into smaller sums that are aggregates at the cluster level. And you take those sums and you look at the variance between them. So you look at between cluster variance. And for stratified designs, you incorporate the strata. So instead of having the variance across all the clusters, you have it within each cluster. You have it That's a high level of Taylor linearization baked into a lot of the software that we use. Alternatively, we can come up with a set of alternative replicate weights. We can create them either through randomization, bootstraps, leave one out, or some design-based orthogonal contrast. They basically do similar things. There's trade-offs. For this talk, we don't really need to worry about that. What you get is you get K sets of weights. So say you have 100 replicate weights. For each weight, some of the clusters have a weight of 0. So it's kind of a leave one out strategy. And the other ones have increased weights so that the total sum of the weights, the population size, is the same. And like before, you calculate your estimates across each replicate, and you look at the variance between them. And with stratified designs, you incorporate the strata. So these two methods now look at variance between the clusters or between the replicates. And that's how we get a sort of a survey design-based estimate. So what are some challenges? So there's two notable trade-offs when you compare these two methods. Taylor linearization has the advantage that you only have to calculate your set of estimates once. Then you just use them as plug-in estimates. Whereas replication methods, you have to calculate a new estimate K times. So if it takes a lot of computational effort to calculate your estimate, you're going to have to multiply that by 100 or 20 or however many replicates you have. So there's a difference in the computational effort. When you use replication methods, you don't have to calculate any derivatives. Whereas Taylor linearization, to get an approximate weighted sum as an approximation to your estimate, you need to take some derivatives, which means that you have to do a lot of analytic work and prep. So the trade-off here is computational effort versus analytic effort up front. So there's some improvements. Cheat a little bit here, but let's talk about abstraction of derivatives, right? So you know there's a few different ways, at least when I was learning it, there were two different ways you could do derivatives. You could do it from symbolic differentiation, or you could do numeric differentiation. Well, it turns out, I just found out about this a couple of years ago, there's something called algorithmic differentiation, which is more at the execution of a computer operation level. There's a paper on this, and it turns out that it's implemented in a few different softwares, particularly in Stan, because they need it to do their Monte Carlo estimation methods that are based on gradients. So the trick is to pull out what's already been implemented. So what that does is you just specify the model, you specify the density, and it creates sort of a black box function that evaluates and gives you the derivative as a function. So that means that there's less work for us to specify the derivatives. We don't have to provide them ahead of time, just the model. And also there's a hybrid approach where you can actually do Taylor linearization for replicate design. So maybe I'll talk a little bit more about that, but the idea is instead of re-estimating the parameter theta, we can still only have a plug-in estimate for theta, and we really calculate the replicate variance of the gradient itself, not the estimate. So here's an example from a recent paper Chance and I have worked on, and we're looking at adjusting Bayesian models to incorporate the survey design. So you use the weight to mitigate the bias. So what we're looking at here is pseudo-posterior. It looks just like a regular posterior likelihood times the prior, except we have a weighted likelihood term here. And what happens is if you just treat it as is and you go through it, the maximum likelihood estimate is a sandwich form, this HJH, which you can think about it as robust or design-based. And but if you just look at the posterior, it behaves as if it's a simple random sample. It just has the model-based one, H. So if you want to go from the model-based one to the robust one, we need to have an adjustment. So I call the R2, R1 adjustment is, I'm calling a design effect. So we can take a square root matrix of the sandwich estimate, a square root matrix of the model-based one, and we can have this transformation here. So that'll get us incorporate the complex survey design. So here's an R code schematic. Those colors didn't come out right. Okay, so it's supposed to be blue, red, and green, but also have good different shapes too, so I'm redundant a little bit. So
that's good for colorblind people.
Yes, exactly. You gotta think, you're 5-way compliant. So the squares, the rectangles are the inputs. So we have two inputs: the Stan model that we provide to Stan, thank you, and the survey design variable. So the Stan model will get us. We can the first. You know what? I'm just gonna go for it. Up here, the first oval. This is the estimation part. And then the first diamonds are the parameter estimates, the distribution, and the point estimate. But also from Stan, we can get this function that evaluates the derivative. That's what we need. So from the survey design, the survey package, we can get the replicate, and there's a with replicate function that evaluates whatever function you want across the replicate. So from these two, we'll get the two components that we need to get the sandwich estimate to apply the adjustment. The reason why I have this schematic is not so you memorize it, but just so if you look at the code that's included with this paper, you'll be able to sort of walk through it. So at a high level, we're doing some tricks to incorporate the survey, complex survey design into the various components for sort of arbitrary models, not just ones that are built in. So that's it. Thank you.
Does anyone have a question?
So, do you have any information about like the performance?
Sure. So the question question is, what is the performance relative to the other two methods? So it's sort of like how we implemented it is it's basically the Taylor method. So it's faster than a traditional replicate method, but not all surveys have the clustering information. Some of them just provide you replicates. So it's a way to kind of do both. If you're just doing simple means, it wouldn't really be any advantage. The advantage is if it takes you a lot of effort to come up with a formula. Thank you very much.
Next up, we have Keith Finlay and Elizabeth Rohide, automating maintenance of public sector survey firms.
All right, thank you. And there's the, and thank you, Matt, for speaking into the phone with the question, especially.
Hi. So today I was looking at the session. This is a little bit more statistical production oriented in terms of like process automation. I'm going to talk about trying to automate maintenance of public sector survey frames. I work in the Economic Reimbursable Surveys Division at Census. We do reimbursable work for other federal agencies. And this work comes from some of the collections that we do for DOJ. So these collections tend to be targeted at like facilities, so like a juvenile residential facility or a prison. And so the frame here, the unit would be a facility or a government unit. And then a frame is our universe file. For those of you that aren't familiar, it's the list of people we contact for a sample or a census. And so the information on the frame would be like the name, the contact information. It may also have unit characteristics, so if it's trying to figure out if something's in scope or in universe. And the staff that work on these collections generally do all of this by hand. So they do these things annually. When new information comes in, they pull up two windows in Excel, and they look at the left side and the right side, and they try to see what was in last year and what might be new, what's changed. Because these are public sector collections, most of that information is probably online already. And so in this project, there's a few things we want to look at doing. So first is try to use web scraping to harvest unstructured data about those government units or facilities. And then the second part is trying to deal with this kind of manual process of comparing new information. So how can we reduce the labor required to integrate new frame, tables, or data? And so we're looking at document parsing and probabilistic matching to try to link new tables into current tables. So this is work that we did over the last 2 summers with, as part of the Civic Digital Fellowship. I don't know if anyone's familiar, happy to talk about it later, but basically it brings in undergrad and graduate students who have like a technical background for work that maybe your unit doesn't have the skills to do. Carlos Ortega, who was our fellow over the last summer, helped us break this problem into smaller pieces. The first year we kind of tried to do everything at once, and that didn't work very well. Everything's in Python. And what we found actually over the last like 4 months is that a lot of these modules, the smaller pieces that we can use for process automation in different areas in our division. And so breaking it apart had these other benefits. So I'm just going to talk about the modules by kind of working through a flow chart of how we figured out this could work. So the first 2 parts are these inputs that we get from the sponsor, in this case from offices in DOJ. So the first are documents with possible frame units. These are basically just like lists. So for the juvenile residential facility, these would be like state compliance lists of facilities they've inspected, that sort of thing. And then the input on the right are tables, but without the unit ID, right? So it's like a list of things we think are in the universe, but we don't have the IDs, so the staff is going and comparing these things one by one. So the first module is just a document parser. So this is like taking unstructured data and trying to get it into the fields that are in our frame. So in this case, it's simple. It's just like name, address, phone number, email. More ambitious would be like unit characteristics. So is it a co-ed juvenile facility, that sort of thing, so that we could look at scope. The next step, so for these tables, it's a little bit more structured. Things are coming in the kind of name, address, phone number fields, but we need to match the candidates, and the names can be different. Department of Labor, comma, Department of something like that. So fuzzy probabilistic matchers. Now, Census has like 3 industrial-grade probabilistic matching systems for people, addresses, and businesses. But what we found is like the people working in this area, these are relatively small frames, 2,000 units. It doesn't make sense to like put all the overhead in that's required to use these other probabilistic matchers. So Carlos built this application that does fuzzy matching in the web browser. So I can like load up the Excel tables from the local machine and do relatively simple probabilistic matching on the local machine. The next thing, because we're kind of just exploring right now, is that we have a lot of human reviews. So we're trying to look at what's happening and making sure we're actually improving things and not screwing them up. But if it looks good, then the idea was that this would get into the frame table. And now we're going to try to think about how we might incorporate public information. So the next steps are going to involve the internet and putting unit information out on the internet. So we want to make sure that we're only dealing with public units, which I started saying is called public sector, but these DOJ units deal with some contractors that run facilities. So it could be private prisons, it could be a contractor that runs a juvenile residential facility. So we don't know, like census policy around web scraping is still ambiguous, so we're only going to deal with the public units in this project. So then originally we didn't have any URLs on the frame, so we used like Google APIs to try to get URLs to link them up to units on the frame. That worked in like 60 or 70% of the cases, so we've had interns kind of hand match the rest so that we can have some high quality data for the next step. Then we take those URLs and we're trying to pull in unstructured data, so we're crawling in these websites and scraping them, and then we're going to try to figure out what we can do with that information later. This process, you can see, is dealing with things that are already in the frame. The bigger problem is how to make sure that we're covering everything in the frame. That means identifying new units that are not in the frame. And so what we've done is we've tried to identify URLs that might have lists of facilities, so it could be professional organizations like Association of Prison Administrators or something like that, where they might be updating their list, and then we could try to incorporate that information. So that's kind of the other side of it. So when you scrape the web based on those URLs and crawling around a bit, you want to filter those pages for relevance. So we use term frequency, inverse document frequency, tools like that for kind of from information theory to identify pages that might have contact information. And then we're back into the beginning of the process. So treat those HTML pages as documents in the way that we treated these other inputs as documents, parse them for those fields that we're interested in, and then match them back into the frame using probabilistic matching. And so the idea is like trying to reuse modules so that we can kind of improve them and spread around the fixed costs of setting up the system. This is all, we're still working on all of this, but we've made a lot of progress this summer. So the next steps are to improve the accuracy of the web scraper, expand the scope from like contact information to characteristics, which is a harder problem, improve the speed and effectiveness of the frame matcher. So if you've done this work, there's a dimensionality problem, and so you quickly run out of memory if your tables get long. So we want to move it over to a server so we can expand that, but still have it be like a like a browser-based interface. And then hopefully move the system into production. On one of these surveys, three full-time equivalents spent 4 weeks matching new information into the frame. And if this works, it would basically run in a few hours. But and then the staff can be reallocated to response and quality improvement. So that's it. Thank you. I'd be happy to take any questions.
Any questions?
Yeah.
As an intern, I used to be an intern, so it's just like a visceral flashback of like the meetings I had.
Yeah.
Were there, like, how bad was it?
The URL?
No, the hand matching.
Oh, well, we even have full-time staff that do this hand matching. It's crazy. Yeah. Yep. Yeah. On one of these collections, it's a single woman, and she spends maybe like 10% of her year hand matching tables over and over again. Part of that is because there's not good frame maintenance on these collections, but yeah. Yeah.
different?
Yeah, it's actually on the,
All right, next up we have John
so
Thomas,
actually,
presenting on ensemble models.
on the home screen, you're going to press that. Yeah, I just,
Oh, like right here?
yeah, right down there, yeah. Great.
Adventure mode.
Yeah.
Okay, I gotta get you out of that, I'm sorry.
Okay.
Otherwise, that's what they see.
Yeah.
Hey, that's more exciting than.
Yeah.
Cool. And let me just put this up here, just in case people aren't hearing. Okay, there we go. That's actually not a bad idea.
Fresh. Sounds like a good idea.
Yeah.
Go. All right, everyone. Hi, my name is Johnny Thomas. I am a second-year master's student at the George Washington University. And today I'm going to present on one of the projects that I've done last year on ensemble modeling in the context of basketball. I'm using a basketball example right now, but this is super applicable in any situation when you're using machine learning or building models for prediction or classification. A little bit about my background. I did my undergraduate degree at Ursinus College, small liberal arts school outside of Philadelphia, and I'm currently at GW. I'm also the president of the student chapter of the Association at GW. Yeah, ASA. In my free time, I watch basketball, and I am a proud fan of the best team in the NBA, the Philadelphia 76ers. That is a fact, not an opinion, by the way. But my presentation today is actually not on the NBA. It is actually on the NCAA and the March Madness tournament. So quick show of hands, how many of you have ever made a bracket in like a bracket pool during the tournament for college basketball? Show of hands, other people that did raise their hands, how many of you won your bracket pool? Oh, yeah? Okay, couple. All right, that's good to hear.
How many of you are afraid to say?
Oh, right, yeah. Maybe some of you can't have certain agreements or whatever, but yeah, so that was a minority of you who actually felt like that did win your pools, and a big reason for that is that the NCAA playoffs are very unpredictable. With the NBA, the seeds tend to end up winning more often than not, but with the NCAA, the players are in their first couple years of their career, so they, you can't really tell what's going to happen, hence the name March Madness. So the question that we had to do was, the question that Google Cloud and Kaggle kind of put together was, could you predict the whole tournament using machine learning? But when we got a hold of the actual competition, it was after the 2019 tournament, so we tried to reframe it. We wanted to do something different. We wanted to see which statistics of a game contributed the most to a win. Which ones, between steals and assists and all the different stats that go into a game afterwards, were contributing the highest to our model selecting the win. And to do that, we needed to create a model that could accurately predict and then classify these games. So every observation in our data set had a game from 2003 to 2019, and we removed all the variables that had any information on baskets made. So just looking at statistics that may or may not indicate if an actual point was made, and seeing if we can classify it as a win without knowing what the actual score would be. So like I said, Kaggle and Google Cloud came together for this competition. I think they do this just about every year. Never in the history of the tournament has someone directly predicted the actual tournament. Hopefully that happens sometime soon. I think Warren Buffett's willing to give like $2 million to whoever can do it. It ain't me yet, though. But anyway, so the data set had games from the regular season as well as playoff games from 2003 to 2019 across 6 data sets that we merged together. Quite a number of observations, as you can tell. Each observation represents one team, so we had to double count every one for the winning team and the losing team and the statistics of each team in each individual game. So it came out to about 26 variables. So we made a bunch of different models, as you can see here, in the various area under curve scores. Logistic regression was surprisingly the one that performed the best. And in a normal situation, or if this wasn't the intention, we could have just stopped here, and we could have said logistic regression is classifying these the best of their ability, but we wanted to take it a step further. And that kind of brings me to my main point of my presentation, ensemble models. So ensemble models are they're fairly new, but at the same time, they're super intuitive and very easy to apply in any situation regarding classification and prediction. Let's use an example with bicycles, all right? Let's say you want to go out and you want to buy a bicycle. You can go to any one of these distributors and go and get a bike, and it's probably going to be a pretty good bike. It's going to do what you want it to do. It probably won't break down on you, and you'll be pretty satisfied. But what if I told you that you could make your own bike? You could grab the wheels from one and the brakes from another distributor and the handlebars from a third and the bell from a fourth one, and you can put them together and make your own bicycle. That's kind of the same way that ensemble methods work. You can take from a bunch of different models the best qualities and characteristics that are classifying and performing the best on the classification and build an outright better model. Let's use another example, all right? Let's say that you are applying for a job. You're applying for a job, and you have 3 distinct interviews, 3 separate interviews that are not related to each other than it's the same company. You're done all of them, and one of them, the first interview you have says that you shouldn't be hired, but the other 2 interviewers say that you're a good hire. Now, alone, if it was up to one of these people, only 2 of them would say that you should be hired, but one of them would say not. But it is the collective decision that you can make the decision on the offer, if this was a majority rules type of situation. Alternatively, it can also look like a unanimous vote for the offer. It really depends on the mechanism that you use when you are aggregating all of the responses. But at its core, that is the same way that ensemble methods operate. It is a collective decision that helps you reduce the bias. When you take into account a bunch of different perspectives from a bunch of different sources, you can create a better model that is much more well-informed, just like in our bicycle and interview example. Now, applying this to our actual, the actual steps, make a bunch of models that have the same, that all predict on a training set, combine the probabilities of each training observation with every model. So every model has a probability that is associated with every observation, and then you want to create a new model that ensembles all of the other models together. That is, you take all the probabilities across every one of the models, and then you kind of do what the interviewers were doing. You look at them as a whole to predict again, and that can be another model as well. And then at that point, it's just the best that you see from those. So going back to the models that we made before, these were the models that we used to carry over for the ensemble because they have to perform fairly well for you to use them. So these 5. What I would recommend, and something that we didn't do, is I would recommend about 10 models for an ensemble method. That's the best way to go about doing it. And then they're going to look something like this. Now, I just kind of simplified this, but this would look like a table full of probabilities. But let's say that each one of these, for every training data observation, has a prediction of a win or a loss for the result. But if you look at an ensemble model, you hope that it can look at them all and accurately predict it much better than they do standing alone. So we made these 4 ensemble models where you can look at them and you can see that they're taking all of the other ones into account based on probability alone. And would you know it that the XGBoost with the ensemble model performed much better than any of the other ones there. And when I say much, that is a relative term. Obviously, every little bit counts when you are shooting for accuracy. So while it is not that great of an increase, not that large of an increase, it still is substantial as far as having the most accurate model. So there are some pros and cons that I did want to address. Pros, obviously, we can increase your accuracy of your model. When you reduce bias, you can then have a more robust model that can better predict when you throw more data at it. This is what, I don't know how many of you guys are following the Kaggle scene, but when Kaggle competitions are won, it usually comes down to the ensemble model. It comes down to people who can get that little extra push, which does go a long way in prediction and classification. And you can also notice different relationships in the data that you might not have seen as one model standing alone. Some cons, it is time consuming. You know, when you do have such a little gain, even though it is substantial, in the sense that it is boosting your accuracy, it is more time that you are putting into model building. And depending on what the project might be, especially in the government, it might be worth your time to plan it out in advance. I know with a lot of cloud services like AWS, this has since been less of an issue, but something to keep in mind as well when planning out your modeling. Interpretability can be challenging. What I mean by that is your ensemble model is based off of a variety of probabilities, not the variables directly. Going from models based on variables and then another model based on probabilities of those models. So it can be challenging if you're presenting to other people, but if you can look at the models at an individual level and find similarities, you can avoid a lot of these issues too. And the third part, and this is probably the most challenging, is that it is hard to find the right ensemble model. There are so many different techniques that you can use over and over again, and even if you use different parameters, it can be challenging to find what is the best fit for the combination of models that you have given it. But it's a learned skill, and I think with a lot of practice you can figure that out. So going back to my presentation, and in summary, these are the statistics that at most came up as most influential towards classifying a game as a win before, without knowing. And a lot of these are defensive statistics. At its core, defense is what is holding down teams to go forward. You know, offense is obviously important, but defensive statistics tend to win championships. And something to keep in mind is that when you have a defensive-heavy team going into the championship, it might be worth your time to put them further along on your bracket. And yeah, that's all I got. So thank you for your time, everyone. Questions? Yeah.
You implicitly referred to the variable importance in the last slide.
Mm.
Do you have any handle on it? Because a lot of these techniques go out with variable importance.
Yeah.
But when you combine them together.
Right. Yeah. So, and this is kind of a different part of our study, but when we look at all the variables at its core, like I said before, because the ensemble itself looks at the combination of the probabilities, it can be challenging to look at the variables from the ensemble. So what instead we did is we looked at each model that was contributing to the ensemble method and saw what was common between those, which variables were always coming up in these particular models that we had. So we kind of had, but that's another step in the time-consuming part, right, where we had to go back and see, okay, the ensemble model is heavily dependent on this one model that is being used in it. So that was, yeah, so another step that we had to do. But, you know, with a fine-tooth comb, you can find that information, yeah.
So a lot of times with ensemble models, I think there's something, as you say, all that last little bit of juice out of your data. Thoughts about, you know, as we ran this model post-hoc, you know, if we would use it to predict next year. Do you still think an ensemble model would do better?
I tend to think that, yes. I know overfitting is definitely a concern that's common as well. But because, and this comes down to how many models you use too, right? Where if you see commonality across a bunch of different models, you can combat that. And it kind of gives you like, we got like 0.008 increase. And that is so low because we are really using a fine-tooth comb to see what actually is significant and what can help us avoid the overfitting. So I think that it is important to keep it in mind, especially when you choose the models to enter your ensemble. But at its core, I do think that it does check for a lot of these things too. Yeah.
Probably said this and I missed it, but how did you get the final vote? Was it a majority vote across the models?
Yeah, so
like for the final winner.
Yeah, so what we did is we took the probabilities of all of our models and we ran these four methods on them. So we took all the probabilities and we did XGBoost, logistic regression, random forest, and another XGBoost with new parameters. And that's kind of the tough part of ensemble methods is that you need to kind of pick and choose how you want to do it, rather boosting or bagging methods, or another one of the techniques that are very similar to one that we use. So yeah, and trying as many of these as you can is probably the best way to go about doing this. But at its core, you just want to increase that AUC without overfitting. Yeah.
What are some not so obvious mistakes beyond
yeah, and that's something that I'm also working with too. As a second year master's student, I think that it is challenging to know what the best things are. I think a lot of times you really just got to look at the data and you got to see how it's behaving and use as many models as you can that are performing fairly well. If they're in the general ballpark of the same area, all the ones that we use from XGBoost up are about 93 to close to 94. And I guess just kind of having as many models in the same range where you think that the next only thing that you can do now is try and put them together. Working as hard as you can. Like I said, if I were to redo this project, I probably would have done 5 more, and that probably would have helped out a lot of the way. Thank you. Yeah. All right, thank you, everyone.
So do we know who the next one is? Spencer?
Okay. Yeah. So next up, we're going to have Marianne Spencer and Brigham Bastion, text analysis of death certificates.
Hi, everyone. So we're going to be co-presenting today. So I'm Marianne Spencer. And
Brigham Bastion.
And our presentation today will be on text analysis of death certificate records to ascertain drug involvement in deaths using the National Vital Statistics System. I'm sorry. Talk a little louder.
Okay. Actually, you could use the mic. I forgot there was a mic there.
Testing.
Wait, we have to. There we go.
Testing. Okay.
This room is really, the air handler is really loud.
Sure.
Thank you.
Okay, so just briefly, and just before we start, I wanted to mention we did, in the interest of time, start at a high level. So if there's anything about our methods that you want us to dive into, feel free to reach out to us later. But ultimately, I wanted to give an introduction to the National Center for Health Statistics, which provides statistical information that guides actions and policies to improve the health of the American people. And we manage several data systems, one of which is the National Vital Statistics System, which encompasses the processing and coding of birth and death certificate records from 57 jurisdictions, which includes the U.S. states, New York City, District of Columbia, and 5 U.S. territories. And for the mortality component, when we're assigning cause of death information, we categorize them using ICD-10 codes and assign, and after the coding, process this information and disseminate them for health statistics, surveillance, and other research purposes. In the figure here, we have a couple examples of some of the statistical reports we issue out at NCHS, and this is the data source that we use for mortality. So this is the death certificate, and it includes demographic and medical information. The demographic component of the death certificate is typically completed by a funeral director using information from the best qualified person, being the spouse, parent, child, or other relative. And the medical component, which is the part that we use for our analyses, is either completed for natural causes of death by the attending physician, nurse practitioner, or physician assistant, and for sudden and unexplained deaths, for instance, an injury or suicide death or a drug overdose death, for the case for our analysis, is completed oftentimes by a medical examiner, coroner, or justice of the peace. And so this is an image of the U.S. Standard Death Certificate, cause of death section. And when we're referring to that information written by the medical certifier that provides the cause, manner, circumstances, and factors contributing to the death, we refer to this as the literal text. And so those are these red sections here. The top image is the part 1, the chain of events that directly cause the death. Part 2 is the significant conditions contributing to the death. And the very bottom red box there is an open text field where the certifier can provide a description of how the injury occurred.
Okay, so as Marianne said, death certificates, we use ICD-10 codes to codifier to tell us what's going on in death certificates. And you can see these 4 ICD-10 codes right now on the screen. We've got T40.1, which specifies heroin, and another ICD-10 code, T40.3, called for methadone. But we have these other codes that are just sort of general categories, classes of drugs, natural, semi-synthetic opioids, and synthetic opioids other than methadone. And so, we can see that sometimes drugs will, overall it might be going up, but drugs might be going up or down or just staying the same inside. So we want to know more about what's going on. So we had to start doing these text analysis little by little. So these are examples of what we might find inside these general categories of drugs. Opioids, stimulants, benzodiazepines. Especially we want to know what's happening with the fentanyl. We have fentanyl itself, which will have a death certifier stage, fentanyl. But a lot of the death certifiers will go into much more detail and specify these analogs, and this is just a small list of the fentanyls we've seen. And then we want to really look at our methods and develop something that will be informative for anyone who wants to look at this, because we want to eventually go to publicize this to make sure everybody knows what's going on. So we work with the FDA, and the FDA actually created some methods for us. And first we pre-process the text, and the FDA didn't want to do this at a very micro level. And so they removed stop words, special characters, and then sort of like stream by stream, they examined the terms. Sometimes it was 2 words, like acetylfentanyl. All this was codified and presented as a principal variant. You might see fentanyl and a misspelling of fentanyl, but it would all be coded to one drug. And then we also want to look at the context of the drug. So it might say, fentanyl overdose, not heroin, or history of heroin, and these things are very important when we're looking at drug overdoses. And so the details of this can be found in this methodology, the drug measurement involvement, DMI methodology.
So as Brenna mentioned, this drug mention with involvement methodology is what we use, and have several published papers on it. But what I wanted to give very briefly is some official statistics that we've issued out that use this methodology and applied it to the literal text field, and show some examples of some of the things that you can look at. So as in the slide that we had shown with some of those fentanyl analogs, there could be multiple misspellings. Death data can be fairly messy. And so while it looks like on this left-hand side you can see age-adjusted rates for drug overdose involving fentanyl by sex, but this will include those misspellings, those fentanyl analogs, and fentanyl, and you can look at rates over time from, in this case, 2011 through 2016. On the right-hand side here, this other table is another example of what we can use using this methodology. And so this one here shows the drugs that were most frequently mentioned on death certificate records. So here you can see in 2011 the relative ranking of what were most frequently mentioned on death certificate records, and juxtaposed to it on the right are the most frequently mentioned drugs in 2016. And what's interesting is now that we're getting into this type of granularity, we can see how the ranking changes. So for instance, if you look at oxycodone, which is ranked as number 1 in 2011, we can see that it's changed ranking to rank 6th by 2016, whereas for instance fentanyl in 2011, which was the 10th ranking in 2011, it jumped to the first ranking slide in 2016. So in summary, with this methodology and with this examination of this unstructured data to look at the literal text, this can enable us as researchers to report with more granularity the specific drugs involved in death. Of course, this comes with several challenges. One, for instance, the identification of these specific drugs are dependent on the testing, interpretation, and reporting of death certifiers. So in other words, if a death certifier does not report it or write it down on the death certificate, of course we can't identify it on the death certificate record and therefore report it. So that's a critical challenge for us. Also, we've been finding that the reporting of specific drugs reported on death certificates have been improving over time. So temporal changes can impact trends analyses. So that's another consideration that we would have to look at when we're reporting official statistics on this. So in the future, some steps that we're looking at is how do we automate these processes. There's new terms, especially when we're looking at these illicit drugs, new misspellings, all these other terms. What are the methods that we can we incorporate machine learning to identify these new terms? And while recognizing that we must identify terms that might be only showing up on death certificates a small number of times, we can't really make like unsupervised learning. This will always be some type of level of supervised learning to identify these fentanyl terms. So those are some of the things that we're looking at future steps. So that's the high-level version of our project. Here's our contact information, so if you have any questions, feel free to reach out to us.
I just want to mention Marty here. She's been guiding us, and it's going to sound so much along the way. She's a gene panelist.
Anyone have questions?
So you said you.
So you said you looked at the context. Were all those steps done by hand? And then you also did, I guess, sort of collapsed them. You said there was an analog, I think, names for different drugs. So I'm assuming you that'd be easily automated with it. But what about the context? How did you do that?
Okay, so this is where we're showing our dirty underwear, I guess. But most of it was done by hand. When the FDA came in and looked at it, we were able to do some things where say, you know, the word not, for example, once we identify that word, we don't need to identify it again. In a way, it's not necessarily the context that was reviewed, it was the individual words. And then a lot of the combinations of words would just drop out from that. And then in addition to that, as the time went on, we kind of get more developed as we go from the FDA, we're able to use a lot more advanced techniques to kind of say, you know, we already know some things we can look for and find this place much easier without looking at it.
Kind of incorporating domain knowledge.
Yeah, we can. Yeah.
Okay.
If I understood correctly, you're looking at death certificates without the ICD-10 cover.
Yeah, just
because what would also be interesting is knowing specific drugs and those ICD-10 potential.
Oh, yes, of course. We actually do that where we say we've got this system that's looking for all these drugs in the death certificates, but then for our publications, that's exactly what we do. We say what are the drugs we found in certain ICD-10 codes.
And just to give an example, one of the T codes that Brigham showed on his slide, which is the T40.4, which includes synthetic opioids other than methadone, that includes the fentanyl analogs and fentanyl, but it can also include other synthetic opioids like tramadol. We've done, as part of our analyses, looked at what the composition of that is that might be fentanyl, for instance, and especially in the later years, the majority of that, like more than 96%, I believe, 97% of them are fentanyl, mentions of fentanyl or fentanyl analogs. But those are things that we wanted to, which is part of one of the reasons we wanted to drill into the literal text is to see what that is. So.
I imagine there may also be a bit of double counting when you've got people dying in cocktails.
Yeah, we do this in terms of mention. So if we have seen drug death certificates where as many as 14 different drugs were mentioned, and so you can never take a look at heroin up here on our drink list and see that it's number 2, and then compare that with fentanyl because in most of those death certificates you might be looking at both fentanyl and heroin.
I'm just curious about the time saved from the old method compared to your new method that you're using.
Okay, so we're still developing this new method, so we don't have an accurate count on that.
But can you give like a rough estimate?
Yeah.
Well, there's one project we didn't mention, so we mentioned the future steps. So we are looking at ways to, and this is a project that Dr. Margaret Warner is leading, where we would like to be able to have this essentially already classified and coded, so it's something that will be part of the National Vital Statistics System. So in a way, this is kind of our way. If we can't report with specificity what's on the ICD-10 code, a way of reporting it now, but it is, as Bergen said, still a long process until we get it fully automated or less time intensive than what we're currently doing.
I think initially it took like 2 or 3 years to get this up and running, and then probably about a month, 2 months, but it's been much faster recently because we don't have to review new work, old work, just review new work. So, and then we're gonna put on top of this all the methods we're laying in place now. It should be very quick, very quick.
Over time, you've seen a shift in the work time period. How far back do you really feel comfortable going down to like this level of specificity versus like what would you be better served looking at your if we go back a larger number?
So one thing I did want to emphasize is with, like, as you're alluding to with this question, when they write on the death certificate, they might write drug overdose. We'll always know that they are drug overdose deaths. But now, and especially with this push with Dr. Mark Warner, we are trying to get more specific information. So there is efforts in NCHS to get this level of information included on the death certificate. But because we already know that baseline, we will always know what the number of drug overdose deaths. So most of our numbers, when we issue them out, will start around at 2011. We've done preliminary analyses looking from 2010 and back, and we are comfortable with the numbers that starting in 2011. Also, we didn't include it as part of this presentation, but we have done adjustments to where we looked at if the numbers were uniform in terms of those number of drug overdose deaths that don't specify what the drug is, but they do specify that it is a drug overdose death. If they were essentially uniform over a time period, do the rates change? And we found that the numbers are essentially very similar, regardless, at least from 2011 onward. The increase in fentanyl is even that one, which is the increases are very substantial in this time period. The numbers are still fairly stable, and we can report that with the true numbers. So we can, at least from that point, say that, but it is something that we do have to think about, yes.
Are Elizabeth Duncan and Benjamin? No? Okay.
Okay.
That's all with the presentation.
All right. Thanks, everybody out there on WebEx. We'll see you later this afternoon. Bye.